All right, today we're diving into something really cool, a new blueprint for building AI. We're talking about AI that's small, super efficient, but at the same time unbelievably powerful.
For the longest time, the whole game in AI has been about one thing: scale. Bigger models, more data, more and more computing power. But we're starting to see that this approach is hitting a wall. The costs are getting insane and the improvements are getting smaller. So it makes you wonder, right? Have we been chasing the wrong thing all along?
And that question is leading to this huge shift in thinking. The old way was all about brute force. Just scale everything up and hope for the best. The new way, it's all about being smart. It's about clever design and using really high-quality training to get way more out of way less. We're moving from a game of sheer size to a game of smart design.
So here's how we're going to break it all down. First, we'll look at the scaling problem itself. Then, we'll introduce this new blueprint for efficiency. After that, we'll get into the 3 pillars that make it all work. And finally, we'll talk about why this move to smaller, smarter AI is such a massive deal for everyone.
Okay, so let's start with the big problem. The whole bigger is better philosophy in AI is just not sustainable anymore. We're hitting a wall of diminishing returns where throwing more money and power at the problem just isn't giving us the big leaps forward that it used to.
So, what's the answer? Well, it's this new blueprint for efficiency. And at the heart of it is an approach we can call the mini hybrid model. It's designed from the ground up to punch way, way above its weight class.
And this whole blueprint really stands on 3 fundamental pillars. First, a totally new kind of hybrid architecture. Second, a strict quality-first diet of data. And third, a seriously advanced optimizer that makes the whole thing hum. Let's take a look at each one.
First up, the architecture. This is the skeleton of the model, right? And it's where all the smart design really begins.
To understand why this is so clever, you have to know about the big trade-off in AI design. On one side, you've got your standard transformer models. They are incredibly powerful, no doubt, but their computational needs just explode as you scale them up. On the other side, you have these things called state space models, or SSMs. They're lightning fast and super efficient, but they sometimes lack that deep, nuanced understanding. So neither one is the perfect solution on its own.
So, what's the brilliant solution? You build a hybrid that takes the best of everything. This TriPath model uses that speedy SSM as its backbone for efficiency. Then, for the heavy lifting and complex thinking, it strategically layers in something called sparse attention, which is a much more focused version of what makes transformers so powerful. And to top it all off, a mixture of experts network gives it a massive library of knowledge without slowing things down.
Now, this mixture of experts idea is genius. Think about it like this. Imagine you have a huge team of specialists, doctors, engineers, artists, you name it. But when you have a specific problem, you don't ask the entire team. You just call on the 2 experts who are perfect for that exact task. That's what MOE does. It lets the model have the knowledge of a gigantic network, but it only uses a tiny fraction of the computing power for any single calculation. It's how you get that big model brain power at a small model price.
Okay, let's move on to pillar number 2, because having a brilliant architecture is only half the story. What you feed that architecture is just as critical, and that means moving away from just hoarding massive amounts of data to focusing on strategic data quality.
This quote, which is inspired by the thinking behind Microsoft's Phi models, absolutely nails the new philosophy. They discovered you could get these huge jumps in performance not by just endlessly scaling up data, but by creating this really innovative training recipe that's all about data quality. They use carefully selected and even synthetically generated data to really push the model to learn how to reason, not just memorize.
So instead of just dumping a petabyte of random internet text on the model, this blueprint uses a 3-stage curriculum, kind of like how a person goes through school. Stage 1 is the foundation, giving it a broad understanding of language. Stage 2 is a high-quality injection, where it's like the model goes to college, intensely studying the best of the best data, things like textbook-quality code and math, to really sharpen its reasoning. And finally, Stage 3 is all about refinement, making sure those new skills are locked in and the model's performance is stable and reliable.
And now for our final pillar, the engine. This is the tool that drives the entire training process and makes it so incredibly efficient. We're talking about the optimizer, the algorithm that tunes all the model's little knobs and dials while it's learning.
And the number that says it all is this one, 2, as in a 2 times efficiency gain. Let me show you what that actually looks like.
Take a look at this. This chart shows how much computation, or flops, it takes to get to a certain level of performance.
The industry standard, called AtomW, is that big bar. The new optimizer, Muon, is the small one. It requires roughly half the computational effort. When training runs can cost millions of dollars, being able to cut your compute budget in half is, well, it's a game changer.
But, getting this to work isn't as simple as just swapping out one piece for another. The research shows you need to make two really crucial tweaks to make this optimizer stable at a massive scale. First, you need a way to keep the model from basically overlearning and going off the rails. And second, you have to carefully balance how fast it learns across all its different parts. It's some pretty sophisticated engineering, but it's the key that unlocks that incredible 2x efficiency.
So, we've got the three pillars: the hybrid architecture, the quality data curriculum, and the hyper-efficient optimizer. But let's zoom out. What does this all really mean? What's the big picture here?
And here it is. This is the whole recipe, all in one place. You can see how every single choice, from the TriPath architecture and the Muon optimizer to using those mixture of experts, all come together to create something new. This isn't just a random list of parts. It's a complete, deliberate blueprint for a new kind of AI.
And this is why it matters so much to all of us. Building smaller, smarter AI isn't just a cool science experiment. It means that this powerful technology becomes way more accessible to a lot more people. It slashes the cost of developing brand new AI tools. And maybe the most exciting part, it opens the door to having these incredibly powerful AI assistants running right on our own devices, our phones, our laptops, without needing a connection to some massive data center.
So, that leaves us with one last, really big question. For so long, we've assumed that AI power was tied to AI size. But if we now have a blueprint to build AI that is both powerful and small, what does that unlock? What kinds of amazing things are we going to build with it next?